All right, let's dive right into this explainer and uncover the fascinating, honestly kind of hidden mathematical logic behind how we make decisions as a group. Have you ever tried to pick a movie or maybe a restaurant with just three friends, and somehow you ended up in this endless, frustrating loop of disagreements where literally nobody is happy? We interact with voting systems all the time, right? From electing major government officials to simply trying to decide what's for dinner. And we naturally assume that if we just communicate, if we just compromise a little, the right choice is going to present itself. But what if the very foundation of how we make those group choices is fundamentally mathematically flawed? Before we map out the math here, I want you to consider this provocative question, one that completely upends everything we assume about democracy. Is a perfectly fair democratic decision mathematically impossible? We naturally assume that if we just design the rules right, the voice of the majority will emerge cleanly and logically. We think democracy is a solvable puzzle. But mathematics tells a much darker, much more complicated story. In fact, it suggests that this ideal system we're all constantly chasing might actually just be an illusion. To keep us on track through all the mind-bending paradoxes we're about to face, here's our roadmap for this explainer. We'll hit the perfect voting illusion, Arrow's impossibility theorem, the Condorcet paradox connection, a new ternary data proof, Buchanan's realistic critique, and finally, Sen's practical solution. Kicking things off with Section 1, the perfect voting illusion, why majorities fail. Let's look at the search for a perfect voting system and why the math immediately complicates things right out of the gate. Think of majority voting like a giant game of rock, paper, scissors. Imagine an election with just 3 voters choosing between options A, B, and C. It is entirely mathematically possible for 1/3 of the voters to prefer candidate A over B. Another third might prefer B over C. Now, logic dictates that the group as a whole should therefore prefer A over C, right? Because if A beats B and B beats C, well, A should obviously be the ultimate winner. Wrong. The math shows us that the final third of voters can actually prefer C over A, which creates this never-ending cycle. Just like rock beats scissors, scissors beats paper, and paper beats rock. In this scenario, there's absolutely no ultimate winner, just a continuous loop of majorities constantly defeating each other. And that brings us to Section 2, Arrow's impossibility theorem, the mathematical wall. Let's escalate this issue from a simple thought experiment to a universal rule, formulated back in 1951 by the brilliant economist Kenneth Arrow. So the crucial point here is that Arrow established 4 totally intuitive axioms that any truly fair democratic system should theoretically satisfy. Unrestricted domain means every voter can rank choices however they want, no bizarre limitations. Non-dictatorship means exactly what it sounds like. No single person gets to decide the outcome for everyone else. Pareto efficiency means if every single person in society prefers option A to option B, then society as a whole absolutely must prefer A to B. And finally, independence of irrelevant alternatives, or IIA. This one is key. To put it simply, if you prefer chocolate ice cream over vanilla, finding out the shop also sells strawberry shouldn't suddenly make you prefer vanilla over chocolate. The introduction of a third completely relevant option shouldn't flip your ranking of the first 2. These 4 rules, they all just sound like basic, undeniable common sense for a fair democracy. But here is the absolute shocker. Arrow mathematically proved that no voting system with 3 or more options can convert individual preferences into a collective social preference while simultaneously satisfying all 4 of those basic fairness rules. No way. It's not that we aren't smart enough to figure out the right system, or that we just haven't invented the perfect voting machine yet. It's that achieving all 4 simultaneously is mathematically impossible. A perfectly fair system, by our own logical definitions of fairness, literally can't exist. Moving on to Section 3, The Condorcet paradox connection, seeing the cycle. Let's take a step back to the 1700s and see how Arrow's modern theorem perfectly echoes an older, equally baffling mystery. When we look at the profiles of three rational voters ranking three choices, we see exactly how rational individual rankings aggregate into a completely contradictory, endless cycle. You've got voter 1, voter 2, and voter 3 ranking options A, B, and C. Now, every single voter has a totally rational, transitive preference in their own mind. They know exactly what they want. But when you tally them up using pairwise majority voting, basically putting them head-to-head, you get that exact rock, paper, scissors loop we talked about earlier. The group mind becomes irrational and indecisive, even though the specific individuals making up the group are completely rational. This right here is the heart of the Condorcet paradox. Now, for decades, Arrow's theorem has been described as this massive generalization of Condorcet's specific pairwise majority paradox. While Condorcet showed one specific voting system failing in one specific way, Arrow showed that all ranked systems fail universally. But here's the crazy part. Formally and mathematically proving that these two concepts are the exact same contradiction underneath, that remains surprisingly elusive for over 70 years. Mathematicians knew they were related, sure, but they couldn't write the definitive equation linking them perfectly. Why? Because the rigid math of the past didn't account for a very specific, very messy human quirk. Which leads us to Section 4. The ternary data proof cracking the code. This brings us to a captivating new 2026 mathematical breakthrough from the University of Sydney by researchers Livson and Prokopenko. You see, previous attempts to formally link Arrow and Condorcet only worked if voters were forced to have strict preferences, meaning in every single mathematical model, a voter always had to pick a clear favorite between any two choices. But these researchers cracked the formal proof by moving beyond strict binary choices. They introduced what's called ternary data to account for weak preferences. Instead of just a strict yes or no, they used 0 for strictly preferred, 1 for less preferred, and crucially, they introduced the letter E for indifference. This represented that very real human feeling of, I honestly just don't care either way. You like option A and option B exactly the same. Seeing this ternary profile matrix in practice is brilliant. By mapping out this E value for indifference across multiple voters, the researchers could finally capture that missing human element mathematically. It turns out accounting for indifference was the missing key. Once they injected that realistic human apathy into the equations, they were able to formulate a complete airtight proof demonstrating that Arrow's impossibility theorem and Condorcet's paradox are mathematically identical contradictions. If you demand complete fairness and logical consistency, the math forces a contradictory cycle, period. A mystery that stood for 7 decades was finally solved by mathematically defining what it means to simply not care. So, if the math is impossible, do we just give up on democracy entirely? Throw our hands up and accept that group choices are fundamentally broken? Not quite. Let's shift gears to Section 5, Buchanan's realistic critique, a pragmatic escape. James Buchanan, a highly influential economist, pushes back hard against this strict mathematics. He points out that demanding perfect, rational consistency is entirely impractical and unnecessarily restrictive. Look, real human beings are messy. We aren't algorithms. Sometimes we prefer A to B, B to C, and C to A just because our moods change, or the context shifts, or we simply change our minds based on new information. Expecting a massive society of millions of people to behave like a flawless mathematical proof is just setting the bar impossibly high. Buchanan argues that we really shouldn't judge actual human decision-making against an impossibly idealized, pessimistic mathematical model. For example, He points out that universal domain, which is that mathematical requirement that a fair voting system must flawlessly handle any chaotic, bizarre, or extreme combination of votes imaginable, is massive overkill. In the real world, human preferences usually cluster around a few sensible, culturally shared options. We rarely see the extreme edge-case voting patterns that break mathematical models. We shouldn't throw out the entire concept of democracy just because it mathematically fails in abstract, extreme scenarios that almost never happen in reality. Finally, let's look at Section 6, Sen's practical solution, limited consistency. Following Buchanan's critique, Nobel laureate economist Amartya Sen provides us with a highly practical, real-world solution to this whole paradox. Amartya Sen realized that Arrow's theorem only actually destroys democracy if you demand full overall consistency across every possible option all at the exact same time. But Sen proposed a genius modification, limited consistency. If we just relax the demand for total perfection and focus on simple binary choices, pairing two specific options off against each other to see which one the majority prefers in that specific moment, society can still function fairly. Yes, it acknowledges human limits, and sure, it might yield slightly different results if we pair different options tomorrow, but it completely sidesteps the mathematical impossibility. By focusing on practical one-on-one comparisons, it gives us a workable social choice mechanism for our everyday lives. The ultimate takeaway of this explainer is a classic lesson: perfect is the enemy of the good. While a mathematically flawless democracy that never contradicts itself is impossible on paper, a reasonably consistent one that allows for human imperfection is well within our reach. We really don't need absolute mathematical perfection to have a fair, functioning society. We just need a system that works well enough for the beautifully inconsistent humans who actually use it. I want to leave you with this final thought. We've spent this explainer looking at grand social structures and deep mathematics. But think about your own life for a second. If perfect consistency is mathematically impossible, how do your own inconsistent everyday choices actually shape the world around you? Every time you change your mind, every time you compromise or settle for an imperfect choice, you're actively participating in this grand, complex mechanism. Maybe being a little logically inconsistent sometimes isn't a glitch in our system. Maybe it's just what makes us human. Thanks for joining me on this explainer, and keep questioning the math behind the world.